Heyo! Hi, folks. We are moving in my group. We're moving from the electric field near discrete charges, which is to say, like a few point charges. Okay, fine. Look, here's the kind of stuff we've been doing. We've been looking at electric fields made by, here are two discrete charges. We're moving now to fields near continuous charge distributions, like this red line of charge, this uniformly charged stick that ranges in x coordinate from A to B. It has a uniform charge density lambda, defined to be its charge divided by its length. This is a length L. Oh boy. And what we're looking to do is express, so this is a length L. We are looking to express the magnitude and the direction of the field at the origin. So what we have to do is, as opposed to saying there are several point charges, there are here's a point charge, and here's a point charge, and here's a point charge, and if we want the field there, we would say, well, the net electric field is the sum of those individual, it is E1 plus E2 plus E3. What we do now is we add up the tiny little contributions to the field made by, in this case, like this thing and this thing and that thing. Those are all, infinitely small amounts of charge we call dq. And we are assuming this charge is positive, this stick is positively charged, so that dq makes a field at origin, or has a infinitely small contribution to the total field at the origin, that we call dE. And there's like another dQ here, and that has also a contribution that is smaller. How are these different sizes when they're infinitely small? I don't know. But so all of those dQs add to the total field at the origin. And so what we can say is that the total field at the origin is the sum of all the dEs. I'm doing magnitude of right now as opposed to vector field. We'll define the vector field later. Something interesting to point out there. So that this may seem trivial, but it's an important start. Okay, and so how do we define a dE? Well, a dE is if we choose this Coulomb's constant as opposed to the, there's this Coulomb's constant K, which is, if you'd like to write as 1 over 4 pi epsilon naught, you may feel free. K dq over r squared. So those dq's are point charges, and point charges make fields kq over r squared, but these are dq's. Okay, so we're going to add up all those point charge fields. And let's see, dq, right? We've got r as a variable, right? Here's an r vector locating this locating this dq. Here's a different r vector locating that dq. So r is a variable. We have to integrate with respect to a different variable, so we've got to get our dq in terms of r. So we can write, remember that lambda is defined to be q divided by L. So we can say this is the same at, so what I like to do here is say, well, therefore the charge of the whole thing is lambda L, and therefore a little tiny charge depends on that density and, well, dl. So let's see, k lambda dl over r squared. Well, a dl is a little distance this way. There's a dl. We can call that a dr, or we can call the rl. I'm gonna do a couple of things here. One, I'm gonna pull constants out of this integral, k lambda, and now I'm gonna write this as look, r to the negative 2 dr. I'm saying that this dl is a distance along our vector direction. Hello, and our values of r range from A to B. So far, so good. Okay, let's move this to the side. Okay, so let's integrate, and we get E is K. Now, this lambda, I'm going to turn back into Q over L, and we integrate the r squared, r to the negative 2 dr. That's going to give me negative r to the negative 1 from A to B. I prefer not to monkey around with negatives if I don't have to, so I will switch my bounds and switch the sign. Yeah. Okay. E is KQ over. Now L happens to be, well, not happens to be, is defined to be B minus A. Yeah. And look, watch this. We get 1 over A minus 1 over B. That's going to give me E is KQ over B minus A. Now, if I make a common denominator AB, look, this is B over AB minus A over AB, or that. And looky here, isn't that fun? And we have an answer. We have E is KQ over AB. And, well, let's just go one step further and define this field as a vector. Well, notice this, all these DEs point left. So notice that we get we have a positive answer, but that does not correspond, does not correspond in any way to direction. We have to do our own interpretation of the direction of field based on what we know about charges and the directions the fields point relative to those charges. Okay. It's possible that a question may ask for a field in terms of the charge density lambda. I chose to turn that lambda. Into its definition. So that there are a few ways to slice and dice here, but but there's an answer. And what's nice is what this does show something like, well, if this stick is really short, then that means that A is approximately B, or B is approximately A, and what you would get is a KQ over A squared, or a KQ over B squared, and that agrees with what we think it should. So that's nice. Always nice to. That's one of the things I get a kick out of, I guess, is trying to do some interpretation of results. Okay, so. And I'm not sure what how best to wrap this up, other than seems like a redundant thing to do, but you may remember seeing some times where if you're not careful about this, I mean, maybe we should say like DE point charge PC. All right, and then we just define a point charge field the same way we did, except for a tiny charge, and yada yada yada. All right, folks. Thank you.